Alright, so we're going to finish up our unit on logarithms and exponential functions. And what we're going to look at is one of the main applications of exponential functions with exponential growth and decay and modeling data. So one of algebra's many applications is to predict the behavior of variables. This can be done with exponential growth and decay models. With exponential growth or decay, quantities grow or decay at a rate directly proportional to their size. Populations that are growing exponentially grow extremely rapidly as they get larger because there are more adults to have offspring. World population and the balance in an account subject to continuous compounding are special cases of exponential growth models. So the mathematical model for exponential growth or decay is given by A equals A sub 0 times e to the kt power. So if k is greater than 0, the function models the amount or size of a growing entity. A sub 0 is the original amount or the size of the growing entity at time t equals 0, and a is the amount at time t, and k is a constant representing. So a sub 0 is always our starting amount, and a will always be our final amount. If k is less than 0 or negative, then we're looking at a decaying entity. So sometimes we need to use given data to determine k, the rate of growth or decay, and after we compute the value of k, we can use the formula a equals a sub 0 times e to the kt power to make predictions. So, the United States population in millions for 5 selected years, so we automatically know that, so 5 selected years from 1970 through 2010. In 1970, the United States population was 203.3 million, and by 2010, it had grown to be 308.7 million. Okay, so since this is our first year, the 1970, the 203.3 is going to be our starting value, and 308.7 is going to be our ending value. We can find our t by subtracting the years. So how many years have gone by from 1970 to 2010, and that would be 40. What we don't know is our k. So find an exponential growth function means that we're going to have to find k first. So if we plug everything into our formula, so a is the 308.7 equals 203.3 times e to the k, which is what we don't know, times 40. So we're going to divide 203.3 on both sides. And since we're going to get a decimal when we divide those, I'm going to just leave it the way it is. Equals e to the 40k power. And then we're going to natural log both sides, because when we natural log and e are going to go away. So we have 40k equals the natural log of the quantity 308.7 divided by 203.3. And to get k by itself, we're going to divide by 40. So k equals the natural log of 308.7 divided by 203.3 all over 40. And I'm going to actually show you guys how to plug them in the calculator since I know some of you are having some issues. Okay, so we have natural log, and it opens up your parentheses, of 308.7 divided by 203.3. Make sure you close your parentheses and then divide it by 40. Okay, so this is approximately 0. We're going to round 4 decimal places. So 0.104. So our model would be A equals our starting value, 203.3, e to the 0.0104 times t power. So now we can determine, so by which year will the United States population reach 335 million? So this is what we're wanting to end with, and which year, so it means t is what we're trying to find. So we have 335 equals 203.3 e to the 0.0104 t power. So we're going to go through the same steps. So we're going to divide by 203.3. Then we're going to natural log both sides. And then divide by that 0.0104. So the natural log of 335 divided by 203.3, all divided by 0.0104. Okay, so if we plug that in, divided by that 0.0104, we get approximately 48. Okay, but it says what year? So our starting year was 1970, plus the 48 years we just found is going to be 2018. So that would give you your year. All right, so another example, so that was showing growth. So if we want to look at decay, one of the common exponential decay functions is looking at the half-life of a substance. So the first thing we're going to look at is carbon-14. So we're going to use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount. Okay, so when it says half the original amount, that means our final is going to equal half of a sub 0. So we don't need the starting amount, we can just use that idea. So to find the exponential decay model for carbon-14. So we're going to plug in what we know. We're going to use that same formula we did on the first page. So we're still using A equals a sub 0 e to the kt power. Here our a equals half of a sub 0. Oops. K is what we need to find, and our years is 5,715. So when we divide by a sub 0, that starting amount that we don't know how much it is, what's nice is it cancels out. So we're left with 1/2 equals e, the 5,715 times k power. We're going to natural log both sides. So we have the natural log of 1/2 equals 5,715k. Divide by the 5,715 on both sides. And we find that k equals the natural log of 1/2 divided by 5,715. So natural log of 1 divided by 2 divided by 5,715 gives us negative 0.000121. And I always try to go to at least 3 decimal places past the zeros. So our function would be a equals a sub 0, so whatever our starting amount is, times e to the negative 0.000121 times t power. So now this will work for any type of carbon-14 value that you have. Alright, so in 1947, earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab Bedouin herdsman. Analysis indicated the scroll wrappings contained 76% of their original carbon-14. Estimate the number of Dead Sea Scrolls, or the age of the Dead Sea Scrolls. So, we found that it had 76% of the original. So that means that A equals 0.76 of the original. So we can plug that into our formula that we have. From up above that we just found. Divide by the A sub 0. It's going to make those variables go away. So we have 0.76 equals E to the negative 0.000121 t power. Natural log both sides. So we have the natural log of 0.76 equals negative 0.000121 t. We're going to divide by the negative 0.000121 on both sides to find that t equals the natural log of 0.76 divided by negative 0.000121. Make sure you close your parentheses. And we get 2,268 years. So that's how old those Dead Sea Scrolls were. Alright, so if we change our chemical, so now we're looking at strontium-90 as a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones. The half-life of strontium-90 is 28 years. Okay, meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. Find the exponential decay model for strontium-90. So, half of the original amount means that our A is going to still equal half of A sub 0. And A sub 0 times E. K is what we want to find, and our time is 28. So if we divide by A sub 0, we have half equals E to the 28 times K power. We're going to natural log both sides, so we get natural log of 1/2 equals 28K. If we divide by 28, K equals the natural log of 1/2 divided by 28. If you plug that in your calculator, we get approximately negative 0.025. So A equals A sub 0 E to the negative 0.025 times T power. So suppose that nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take for strontium-90 to decay to a level of 10 grams? So 10 is what our final amount is, equals our starting amount is 60 times E to the negative 0.025 T. So if we divide by 60, we get 1/6 equals E to the negative 0.025 times T power. We're going to natural log both sides. And then divide by the negative 0.025. Okay, so natural log 1 divided by 6 divided by negative 0.025, and we get approximately 71.7 years. Okay, so the last way we can see applications of our exponential growth models is, so from population growth to the spread of an epidemic, nothing on Earth can grow exponentially indefinitely. Growth is always limited. So we have the logistic growth model as a function used to model situations of this type. The mathematical model for limited logistic growth is given by f of t, so a function of time, equals c divided by 1 plus a times e to the negative bt power, where a, b, and c are constants, with c and b greater than 0. So as time increases, the expression a times e to the negative bt in the model approaches 0, and a gets closer and closer to c. This means y equals c is a horizontal asymptote for the graph of the function. Thus, the value of a can never exceed c, and c represents the limiting size. So that's the key thing. So c, whatever is in your numerator, that's your limiting size, meaning that's the highest it can go. So we're going to look at an example and it'll make a little bit more sense. So the function f of t equals 30,000 divided by 1 plus 20 times e to the negative 1.5 t power describes the number of people, f of t, who have become ill with influenza t weeks after its initial outbreak in a town with 30,000 inhabitants. So how many people became ill with the flu when the epidemic began? So when it began, that means the time is 0. So we're going to just simply find f of 0. So we have 30,000 over 1 plus 20 times e to the negative 1.5 times 0 power. So if we plug that in, we have 30,000 divided by, make sure you put parentheses around your denominator, so 1 plus 20 times e to the negative 1.5 times 0 power. Okay, and we're going to round, so we get 1,429 people. So if how many people were ill by the end of the 4th week, so that means now that t equals 4. So we have that 30,000 divided by 1 plus 20 times e to the negative 1.5 times 4. So an easy way to get straight to your answer rather than having to retype the whole thing, if you hit second, enter, it's going to bring back what you previously typed, and just use your arrows and delete the 0 and put the 4. So we have 28,583 people. Okay, and then what is the limiting size of f of t, the population that becomes ill? So, how many people were in this town? 30,000. So think about it. Can you have more than 30,000 people become ill? Well, no, because there's only 30,000 people. So that is your answer. 30,000 people. It will always be the same as whatever is in your numerator.